We are going to learn about column chromatography and HPLC, which is high performance liquid chromatography, or sometimes called high pressure liquid chromatography. We're going to talk about the different type of columns used, the equipment, and how these are used to separate proteins. And these proteins are used to study HIV and to come up with different types of drugs to fight HIV. Column chromatography and HPLC are used to separate mixtures. They are used specifically in this unit to separate proteins and enzymes in HIV research. HPLC is column chromatography, it's just aided by pressure. High pressure liquid chromatography or high performance liquid chromatography is shown in front of you. These are the parts of the machinery. And you start with your solvent, which is your mobile phase. It goes through a pump that's going to pump our solvent, and here is our injector where we put in our sample. It's going to pump our solvent and our sample through our column. And high pressure liquid chromatography is basically column chromatography. The only difference is in this column we have a much smaller solid stationary phase. So in regular column chromatography it's around 100 microns, and in high performance liquid chromatography it's around 3 microns. Gravity would not be able to force our solvent and our sample through this small size of our stationary phase, and so we need pumps to do that. And then once it is separated in the column, it goes through a detector, and we'll go over what the different detectors are, but this is a general chromatogram, and you can see the different parts coming through at different times and then on to our waste. HPLC is a form of column chromatography, so we're going to focus on these columns. And here is a column that's filled with a stationary phase. Right here, this is a solid stationary phase, and just like the paper chromatography that we've explored, or the thin layer, polarity is going to be a driving force for the separation of the components in the mixture. So up here we're going to add that mixture, and we are going to add our mobile phase, which will wash our mixture through this column. And the mixture will separate, and then we can collect each sample at the bottom when we're using column chromatography, but this sample is detected through a detector in HPLC, and those detections come out in a chromatogram. Here's just another view of that same column, and I like the labeling here. You can see that the components of our mixture that have stronger interactions with our stationary solid phase will hang on longer in that column, and the weaker interactions will go through faster. The things that come out of the bottom are the eluted molecules. So we are trying to elute our samples through the column, and that is just to remove the target molecule by washing the column with solvents. There are several types of column chromatography. We're going to focus on these 5: size exclusion, ion exchange, normal phase, reverse phase, and affinity. These columns can be used alone, or they can be used in combination to separate different substances. Size exclusion columns take advantage of stationary phases that have pores in them. So when we look at this molecule, this is a molecule of the solid stationary phase, and we have little pores, and the small particles can fit through the pores, and the larger particles have to go around the solid phase media. And the theory is that it takes much faster to go around these particles than to go through all the pores. Again, this is a very simplified view, so it would be caught up in the pores. So what happens is our larger particles will elute first, and then you can see on this chromatogram This is over time on the x-axis. We'll have our larger particles come out first, and then our smaller particles, which take longer to go through those pores, will come out last, and then we can see a definite separation. Ion exchange columns take advantage of particles that are charged. In this example, we have proteins. So here, this blue protein, which is our sample, has more positively charged sections than this red protein, which is more negatively charged. And so for this column, they took resin, which is negatively charged, and that is our stationary phase, and that will attract the positive proteins, holding them in the column longer than the negatively charged proteins. So our negatively charged proteins will elute first. Normal phase and reverse phase column chromatography rely on polarity. On the left, we have our normal phase, and so our stationary phase is going to be a polar solid. And on the right, we have the reverse phase, and the stationary phase is going to be a relatively non-polar solid. In techniques used with HPLC for research on AIDS vaccines and new molecules, reverse phase is more commonly used. And we'll talk about that in a later slide. Let's take a look at the normal stationary phase close up. And as we said, our normal phase is polar. Our general stationary phase is a bed of silicon dioxide that is functionalized. And what that means is N groups are attached to give it more function. So let's look at the N groups here. Here we have our OH attached to silicon dioxide. We have a carbon chain with a cyano group, and here we have a carbon chain with an amino group. And as we go towards the right, we become less polar. So our hydroxyl group over here is the most polar. And this is important because you can choose different columns for different things that you are separating. So if we have a polar compound and a slightly non-polar compound, we're going to choose one of these columns where our target protein is more strongly attracted to the stationary phase. And if we have something that's polar and something that's slightly non-polar, we're going to elute the column first with a non-polar substance such as hexane, and that will elute out all our non-polar substances, and our polar substances will stay back attached to the column. So how do you get that off? Well, we elute the column again with a polar substance that has more affinity to the column than our substance does, and that will kick off our substance, and then our substance will elute off second. And so choosing these columns and your solvents become very important in making the correct column for the substance that you are separating. Here we have a close-up of our reverse stationary phase column, and that would make this stationary phase non-polar. And basically we have what we call a C8 and a C18 column. Our C18 column are used widely in separating proteins, and we'll talk about what that is for our fight against HIV on another slide. But right now, let's talk about the C8 and the C18 column. They're nonpolar because we functionalize that silicon dioxide with a straight carbon chain, so straight hydrocarbon. So a C8 column is called C8 because there is a chain of 8 carbons coming off that silicon right there. And a C18 column right here has 17 plus 1, 18 chain hydrocarbon attached to the end. So our C18 column has a longer nonpolar, what some people call tail, and so that's going to be our more nonpolar, and this is going to attract nonpolar substances over polar substances, and that's when you'd use this column. You just learned how we can functionalize silicon dioxide to make our stationary phase polar, more polar, nonpolar, more nonpolar. We can also take our stationary phase and we can take our solid phase and we can attach a molecule to it. So here's our solid phase, and these yellow portions are the molecules that have been attached to the yellow phase, and sometimes they're referred to as a ligand. So what we're doing now is we are trying to create a stationary phase that has the most affinity to one specific, in this case, protein only, and does not have an affinity to any of the other proteins. So here we have this light blue kind of horseshoe space, and that's going to have the most affinity to this ligand. Actually, in this case, probably the only thing that has affinity to this ligand. So we put our sample in, and when we wash our sample through, the protein that has affinity to that ligand will stick on the column, and everything else will come out the bottom. And then we will elute the protein that we wanted by taking a solvent that will wash off the protein from our ligand, and we'll have a sample that contains only our target protein, and that's affinity HPLC. We do know that the glycoprotein 120 on the HIV virus is used for entry into a CD4 cell. The exact mechanism is still being studied. And so to investigate this, we can do several things. We can purify the GP120, and we can use that to study how it might attach to the CD4 cell. In one study, GP120 was purified using 3 different columns, first an ion exchange column, then an affinity column, and then a size exclusion column. In another study, alternatively, an affinity column was created with GP120 proteins, and substances from the CD4 cell could be run through the column to test the affinity. And these are different ways that the columns are used to study the entry mechanism. In another module, you will learn about inhibitor drugs used in the fight against HIV. Some of these drugs are used to inhibit enzymes protease or transcriptase. So these enzymes need to be purified for this drug research. In order to purify them, column chromatography is used. A combination of ion exchange and affinity columns are used to purify protease. A single or dual system affinity chromatography shortens the purification time of transcriptase from over a week to 3 days. Not only is research being done on HIV itself, but also on the equipment used to monitor and purify substances that are needed for research in HIV. Here's a reverse phase HPLC example where we're going to separate out the different medicines in a cold and cough remedy. So the first thing they're going to do is inject this into the injection port. It's going to go through the column, and then based on polarity, it's going to separate out our substances. And then because they're separated, they're going to go through this detector at different times. And you can see right over here, our chromatograph is showing you 3 different substances coming out at different times. You can figure out the area under the curve to figure out the amounts of each sample, of each different substance in the cough medicine. And so now I'm going to go and talk about the different type of detectors you can add to your HPLC. There are many different types of detectors that can be used with HPLC. Some of the most common ones use light. They can measure refraction, or like our Beer's Law Lab, they can measure absorption. A very common detector used is a UV detector. We've also talked about mass spectroscopy. We've looked at that to determine the average mass of isotopes, so we can get the masses of the substances coming off using mass spectroscopy. Something we haven't talked about is NMR. This gives us a spectrum, and from the spectrum we can determine our molecular connectivity. Sometimes things coming off the HPLC is very, very dilute, And so some people will use a combination of mass spec and NMR to determine very low concentration molecules. One of the ways HPLC is used in the fight against AIDS is in vaccine development. The envelope proteins, the glycoproteins on the outside of the HIV virus, elicit an immune response for us, and so they're used for vaccine development. The glycoprotein 120 has shown the best results so far, and because of this, other envelope proteins are being investigated, such as glycoprotein 145. In order to investigate this, we need a lot of it. So these proteins can be cultured or grown, and we need to monitor the growth of these proteins so we can optimize these results. Reverse phase HPLC has been shown to quantify glycoprotein 145 from cell cultures. In this example, HPLC is used to isolate compounds from plants that are used as anti-HIV agents. Currently in Africa, the plant Nidea sericocephala is used as a supplement to antiretroviral therapy. This plant contains many compounds. One of them is yuanwacine, and it is believed that this inhibits HIV viral replication and reverses HIV latency. HIV latency is when an infected cell lies dormant, so HIV has infected the cell, but it's not replicating. If they can reverse this latency, then the antiretroviral therapy can then attack the HIV that is working. To test this, yuanwacine was separated using many methods together, including HPLC, and then it was tested to prove that it did inhibit HIV and reverse HIV latency. HPLC is a very important tool used in the fight against AIDS. It can separate many small molecules, some used to build vaccine platforms and other used as anti-HIV agents.